Hello friends, here in this video we will see a problem based on shear force and bending moment diagram for a beam which carries all kinds of load, that is there is point load, UDL and even UVL, that is uniformly bearing load. So let us see this question. Here it is given that determine the SFD and BMD for the beam as shown in figure. This diagram is there in front of us. Now here when I look at this beam, it is supported at point A and at point B. The part BD of this beam is overhanging, means after the support here I can say that since the total length of the beam is 7 meters, so it is supported only up to 5 meters. The remaining 2 meter, which is BD, is overhanging. Then there is a point load of 10 kilonewton acting at 3 meter distance from point A or left support. After that, from C to D, that is over 4 meter length, there is a UDL of 2 kilonewton per meter. Then this is called as a uniformly distributed load. After that, there is a triangle, a right angle triangle I can say, and this kind of loading, it is called as uniformly bearing loading or UVL. So this beam consists of point load, UDL and UVL. So for such a beam, we have to draw shear force diagram and bending moment diagram. Let us get started. So in the solution part, here this problem will be solved in 3 simple steps. First, step number 1. Calculation of support reactions. So in this step number 1, I use the condition of equilibrium to get the support reactions. Here first of all, if we see this beam, it is supported at A and B, so the reactions will be at A called as RA, vertical reaction, and vertical reaction at B called as RB. Here there are no horizontal loading, so no need of any horizontal reaction here. Horizontal reaction is 0. Then I'll say that the first condition will be summation of Fy is equal to 0, where upward forces are positive and downward forces are negative. So therefore we have RA and RB as upward, so RA plus RB, they are upward forces. Then minus 10, it is acting downward, minus 10. Next, there is UDL of 2 kilonewton per meter over a length of 4 meters. So this will be converted 2 into 4, so that becomes, now here I'll show it that it is 2 kilonewton per meter acting over a length of 4 meter. Meter gets cancelled out, so this value will be 8 kilonewton, and this 8 kilonewton will be acting downward, that is the point load conversion of the UDL given, so minus 8. Then there is even UVL called as uniformly bearing load, and this is a right angle triangle, so I'll have to find the point load for this UVL also. So here at this side, I'll just draw this UVL and explain. The UVL value is 18 kilonewton per meter and it is acting over a length of 3 meter. So now I need to convert this UVL into point load. So how I will convert this? Since it is a right angle triangle, so therefore the conversion will be half into base, which is 3 meter, into height 18 kilonewton per meter. So this is the conversion. where I am using the formula of for the right angle triangle. Now here this will be cancelled, so it becomes 9. Meter and meter gets cancelled, so we have 27 kilonewton as the conversion of the UVL into point load. Now this 27 kilonewton of the UVL will be acting at a distance of 1/3 from the base. Now wherever the two right angle sides they meet, that point is called as the base and the other one is called as apex. So here we have base and here is apex. So this 27 kilonewton will be acting at 1/3 distance from the base. (27 kilonewton). One-third from the base and 2/3 from the apex. So 1/3 of this base, which will give me the value as 1 meter. So it is 1 meter from the base and 2/3 means it is 2 meter from the apex. So here is the UVL located. I am having the value of minus 27 kilonewton. So here when I am writing, in case of the support reactions, this UVL which I have converted into point load of 27, it will also act in the downward direction. So minus 27 is equal to 0. Therefore RA plus RB will be equal to all these terms. If I add, that comes out to be minus 45. If I send it onto the other side, that becomes plus 45. I will keep this as equation number 1. Next, the second condition of equilibrium, summation of moment about A is equal to 0, where clockwise moments I treat them as positive and anti-clockwise moments are treated as negative. So therefore, here if we look into the diagram, then I am taking the moment at A. Even if we are taking at B, then also it is correct. But if we take the moment at B, we will get the value of RA first. Now I am taking the moment at A, so I will get RB first. So RB is acting upward. When I take the moment at point A, it will be producing an anti-clockwise moment. So minus RB into 5. Then 100 kilonewton, here I have 10 kilonewton, which will be producing clockwise moment at point A, so plus 10 into 3. Then here we have UDL, which is acting at 4 meters, its point load is 8 kilonewton and it will be acting at half of 4, so that is 2 meters. So when I take the moment, the distance between the point load of the UDL and point A, here it is 3 and the point load will be acting at 2 meters, so 3 plus 2, that is 5. So it comes out to be plus 8 into 5. Next, apart from this, we even have this UVL. Now UVL, as we know, from point A, that is the base, it is acting at 1 meter distance. So this 27 into 1, it is producing clockwise moment. So plus 27 into 1 is equal to 0. So therefore, on calculating this, here I will get the value of RB as 19.4 kilonewton. Next, putting this value of RB in equation number 1, put RV is equal to 19.4 kilonewton in equation number 1. So therefore we have RA is equal to 45. Here we have plus RB. If I send it on the right hand side, that becomes minus RB. So minus 19.4. So therefore this subtraction give me the value as 25.6 kilonewton. So these are the values of reactions RA and RB, and here when I have found the reactions, the step number 1 is complete. So now after finding RA and RB, I will show them on the figures. RA is 25.6 kilonewton. RB is 19.4. So when we have found the reactions, we can say that step number 1 is complete. Now step number 2. Shear force, or we can say SF calculations. Now before we go on to SF calculation, we need to have sign convention. So now upward force to the left of the section, downward force to the right of the section. Both are positive. Next, downward force to the left of the section, upward force to the right of the section. Both are negative. So before going on for the SF calculations, we need to have these sign conventions, because without the sign convention we cannot solve any of the problems. So here I'll start with SF calculation from point A. So first, SF at point A is equal to, now at first if we see, if I am taking the section to the left of A, then on the left side of this section we don't have any forces, so the shear force value is 0 on left hand side of A, that is one value of shear force is 0. Next, the other value, for that I will take the section to the right of A, very close to RA. Now if I see this section which is there on the right hand side, to the left of this section there is RA acting upward. So any of the forces which are to the left hand side acting upward must be treated positive. So shear force at A is plus RA, and the value of RA is 25.6 kilonewton. Next, here I have point C. After A, there is point C. Now for point C, first I will take the section to the left of C. So SF at point C. Now taking the section to the left, first of all there will be RA which is acting upward, so positive, plus 25.6. Plus 25.6. Then here, as we know, there is UVL also to the left of the section, and from point A at 1 meter distance, that UVL which is converted into point load is acting, as I have explained here. it is 27 kilonewton. So to the left of the section it is acting downward, so minus 27. So this gives me the value as minus 1.4 kilonewton. Then we will have another value of shear force at point C. SF at point C is equal to, next, now I will take the section to the right of C, that is here, and when I am taking the section to the right of C, I see that to the left there are three forces. First of all RA, then point load of UVL, then 10 kilonewton. RA is positive, the point load 27 kilonewton which is of UVL, that is negative, and 10 is also negative because on the left hand side of the section downward forces are negative. So we have plus 25.6 minus 27 minus 10, this gives me the value as minus 11.4 kilonewton. Then after getting SF at point C, SF at point B is equal to, now we see that the shear force at point C has two values. Similarly for B, I'll first take the section to the left of B. Now when I'm taking the section to the left, how many forces I have? RA, the point load of UVL, 10 kilonewton, and even this UDL which is there up to 2 meter length, it has the same intensity as 2 kilonewton per meter. So this UDL up to C to B will also come here. So I'll write it down that on the left side of B the forces are plus 25.6 minus 27 minus 10 minus 2 into 2, that is the UDL from C to B portion. So this gives me the value as minus 15.4 kilonewton. Then another value of shear force at B, SF at point B is equal to, now for the other value I am going to take the section on the right hand side of B where the value was same up to the left hand side. Only thing is here even RB is there, so this RB which is to the left of this section acting upward is positive, so up to the left hand side of B I'll have this constant value minus 15.4, then plus 19.4, because to the left of the section RB is acting upward, so positive. That gives me the value as plus 4 kilonewton. Next, after this, when I take the section at point D, that is either on the left hand side, if I take the section, and if I will be calculating, I'll get this as up to point B I am getting plus 4 kilonewton. Next, here at point D there is 2 into 2, this much amount of UDL into point load which is acting in the downward direction. So therefore SF at point D will be equal to plus 4 minus 2 into 2, which is the UDL in 2 meter length portion from B to D. So this will give me the value as 0 kilonewton, and it has to be 0 because there is no load acting at the free end. Here this overhanging portion B to D has free end D where no load is there. If suppose there would have been any other load, then the value of SF would have been there, otherwise it is not there as we see here. And even if I take the section on the right hand side of D, there are no forces on the right hand side, so shear force at D is equal to 0. Now I would be plotting the shear force diagram, and for that I have to draw the beam diagram again. So now once I have found out the values of shear force, now I will draw the shear force diagram. For that I will have to draw the beam again, so I am drawing the beam diagram, and below that there would be shear force diagram. So now here we are having this beam which is given in the problem. Next, below this beam we have to draw the shear force diagram and even the bending moment diagram. I will be projecting the points here. Now here, in case of this beam, we have found out RA value. RA was 25.6 kilonewton. Similarly, RB value 19.4 kilonewton. Now below this shear force diagram there should be bending moment diagram, and for that here I will draw a horizontal line as a reference. Now this horizontal line is having shear force value as 0 kilonewton. This line will be the reference for us. Now we will go on seeing the value of shear force. At A, the value is, first value is 0 and the other is 25.6. So it means we have to start with 0 and then go up to 25.6 kilonewton. Now here I have one value of shear force at point C, 25.6 kilonewton. Next, at point C, first the value is minus 1.4 kilonewton, so it will be below this line. .4 kilonewton, it is negative, so below the line. Next, again at point C we are having another value minus 11.4, so this 1.4 will go on increasing and it will reach up to a value of 11.4, which is negative. Then at B again there are two values. First minus 15.14, so minus 15, which will be below 11.4, so minus 15.14, 15.4 it is kilonewton. Then it goes into positive region, that is plus 4 kilonewton, so plus 4 kilonewton. Now at D the value is 0, so I need to connect these points. As we see, there is UVL from A to C, so whenever we have UVL in the beam, the shear force diagram should have parabola. So here between A to C, that is connecting 25.6 and minus 1.4, there should be a parabola. Which should connect plus 25.6 and minus 1.4. Then this minus 1.4 increases and it goes up to minus 11.4 kilonewton. After that at B the value is minus 15.4. So there is UDL between C to B. So wherever there is UDL, the shear force diagram should be an inclined line. Then from minus 15.4 it goes up to plus 4 kilonewton, plus 4, and again as we see from B to D there is UDL, so shear force should be an inclined line. It is an inclined line. Now whatever we have plotted above the line, that is positive, below the line, that is negative. So this is the shear force diagram where we are having parabola from A to C. So here I will mention that there is parabola from A to C. Now this is the complete shear force diagram, and as we see there is a point where shear force crosses positive to negative region, and here there is one point where SF is 0. So where this SF is 0, the bending moment will have maximum value. So going on to step number 3. It is bending moment calculations, and again for bending moment calculations also we should have the sign convention first, without which we cannot solve the problem. So clockwise moment to the left of section, anti-clockwise to the right of section, both are treated as positive, and this is called as sagging. Bending moment. Then anti-clockwise moment to the left and clockwise moment to the right, they both are treated as negative, and that is called as hogging bending moment. So now, here I am calculating the bending moment. As we see, the given beam is an overhanging beam in which portion BD is overhanging. So first of all, moment at A will be 0 because it is supported. We don't have any part of the beam ahead of A, so there won't be a moment. So moment at A is equal to 0. Moment at A is equal to 0 since it is supported. Next, moment at D is equal to 0. Now moment at D is equal to 0 because it is free end. We don't have any load which is acting from here. So at D the moment will be 0. But at B it won't be 0 because after B we have some part of beam which is extended. This BD portion is there. So there will be moment produced because of this load and distance. So moment at B will not be 0 but at D it is 0 since it is free end, or we can say overhanging. Next, now we have moment at point C. This point C, if we look at here, then to the left of C the forces are less as compared to the right hand side. So for the calculation of moment we have to see that how many forces are there so that the calculation becomes simple. So to the left of C there are less number of forces. Now if I see on the left of C, because of RA, the moment which is produced will be, RA is acting upward, so when I take the moment at C, the moment will be produced in clockwise direction. So to the left, clockwise direction or clockwise moment is treated as positive. So plus 25.6 into the distance between A to C is 3 meters into 3. Next, there is even the point load of this UBL which we have found out. That point load of the UBL is 27 kilonewton. This is end A and this is C. So from C its distance is 2 meter and the value is 27, and here it will be producing anti-clockwise moment at C. So to the left of C there is anti-clockwise moment because of UVL. So anti-clockwise moment to the left is negative, so minus 27, which is the point load of the UVL, into 2. So from this I'll get the value of moment at C as plus 22.8 kilonewton meter. Next, after this we have point B. So moment at point B will be equal to, now if I check here, to the right of B there is only this much amount of UDL which is of 2 meter length. So the calculation will be easy when I take the right hand side forces now as compared to the left hand side, because here there are more number of forces, so we have to select in such a way that there are less number of forces for the calculation. Now if I look in portion BD, there is point load of this UDL which is 2 into 2, and that point load will be acting at half, that is half of 2, which is 1 meter. So when I take the moment at point B, that moment will be in clockwise direction and it is to the right of B. So to the right clockwise moment is treated negative, so minus 2 into 2, which is the UDL into the distance, that is 2 kilonewton per meter multiplied by 2 meter, so that gives me 4 kilonewton and this 4 kilonewton will be acting at half of 2, because for UDL it is acting exactly at half, produces anti-clockwise moment, so minus 2 into 2 into half of 2, which will be 1. So therefore the moment at B comes out to be minus 4 kilonewton meter. So now, if I show these points on the bending moment diagram, it will be drawn just below the shear force diagram. Here this horizontal line has 0 kilonewton meter bending moment. Now bending moment at A is 0, at D it is 0, A and D. Next at C it is 22.8, which is a positive value. So at C it is 22.8 kilonewton meter. Then at B the value is minus 4 kilonewton meter. Minus 4 kilonewton meter. But now here, after having these 4 values, I will not be joining them, because if we see here, there is a point where shear force becomes 0 when it is crossing from positive to negative, as I have told here. So at this location, SF, that is shear force, is equal to 0. So wherever shear force crosses its line, crosses the horizontal line from positive to negative or from negative to positive, the value of shear force is 0. At that point, bending moment will be maximum. So these projections which I am taking, this will be for the maximum bending moment. And now for this calculation of maximum bending moment, first of all I should know that at how much distance the shear force is becoming 0, then only I can find the bending moment at this location. That is here, I'll say that from point C, this location of 0 shear force is at x meter distance. So this is at x meter distance. So now here we would be calculating the maximum bending moment where SF is equal to 0. Now here, as I have located with respect to C, I have given the distance x, but here I'll make a small change. Instead of taking it from C, I'll take the distance x with respect to point A. That is, here we are having 3 minus x. I will replace this and make this distance as x. I'll be making this distance as x. So when this is x, the total distance is 3. So the small amount of distance here will become 3 minus x. So this is 3 minus x. I'll find the distance with respect to point A. So calculation of maximum bending moment Now as I have taken the distance x with respect to point A, and this remaining is 3 minus x, because the total distance is 3 meters. So now I'll find the value of UVL here, that I'll denote it as W, kilonewton per meter. So from the similarity of triangles, here I'll say that it will be height upon base, that is 18 by 3, is equal to, here this height is W divided by base is 3 minus x. So therefore W will be 6 into 3 minus x in terms of kilonewton per meter. Now this much is the UVL acting at the distance where we want to find this value of x. So now I'll say that the calculation of shear force will be done over this section. So hence summation of SF is equal to 0 at that section. So therefore we have, to the left of this section we have 25.6, which is upward, so positive. Next, now we also have at this section x from A, there is small UVL. The value of this UVL W is 6 into 3 minus x, we have found out. So that will be minus, I'll convert that UVL into point load, so half into, this will be the height, which is 6 into 3 minus x multiplied by the base, which is 3 minus x. Is equal to 0. So therefore here this 2 and 6, they will get cancelled out, and I'll have the equation in the form plus 25.6 minus, this will be 3 into 3 minus x whole square is equal to 0. So therefore minus 3, here this will be plus x square is equal to 0, that is a minus b whole square. Now multiplying 3 inside, so that will give me 25.6 minus 27 plus 3 into 6, that is 18x minus and plus minus 3x square is equal to 0. So therefore minus 3x square, if I send it onto the other side, it becomes plus 3x square. 18x onto the other side minus 18x. 25.6 minus 27, that gives me minus 1.4, send it onto the other side, so becomes positive. So therefore on solving this equation, hence therefore on solving we get the value of x is equal to 2.317 meters, and this is with respect to point A. So we have found out the location where shear force will be 0. And that location is from point A, it is 2.317 meter. Now I'll find the distance from C as well. So therefore x is equal to 3 minus 2.317, which gives me the value as 2.317 it is 0.683 meter with respect to point C. So now we need to calculate the maximum bending moment at this point, which is located at a distance of x, which is 2.317 meter from point A. I need to find out the value here. 2.317 meter. So I will be taking the moment at this section, so that will be called as maximum bending moment. So hence maximum bending moment, m suffix max, will be equal to, now if I see here, this is my section, to the left of that RA will be producing clockwise moment. So clockwise moment to the left is positive, that is plus 25.6 into 2.317, then minus, after this we have this entire UVL whose point load is 27 kilonewton, and that will be producing anti-clockwise moment. So minus 27 into, now the distance, here I want this section, the point load of the UVL kilonewton is located at a distance of 1 meter from A and 2 meter from C. Meter is from C. Now I want the distance from this section up to the load, so that will be 2 minus this distance is 0.683. So from 2 I'll subtract 0.683, that will give me the distance. So therefore on calculating, I'll get the maximum bending moment as plus 23.76 kilonewton meter. And now this maximum bending moment I will be plotting onto the diagram. So 23.76, which is a positive value, kilonewton meter. So now after finding the maximum bending moment, now I will draw the bending moment diagram. As we see here, there is UVL from A to C. So wherever there is UVL, shear force diagram is a parabola. Bending moment should be a hyperbola, or also called as the cubic curve. So I will join this from 0 to maximum, that is 23.76. Then it reduces up to C, which is 22.8 kilonewton meter, and within this region this curve is cubic. Cubic curve from A to C. Next, here if we see from C to B there is UDL, so 22.8 will be joined to 4 with the help of a parabola, because since there is UDL, shear force is an inclined line, bending moment should be parabola. Then again from B to D there is a parabola, so from 4 it will go up to 0. Parabola from C to D. Whatever I have plotted above the line, that is positive whatever I have plotted below the line, that is negative. So here is the bending moment diagram. So as it was asked in the problem, we had to draw the shear force and bending moment diagram for the beam given, and here we have completed this, and with this we complete the problem.